functions, take a little more thinking. The exponential functions did. So the idea is, if f of x is b to the x is 1 to 1, it should have an inverse function. To find an inverse, we let f of x, just call it y, then we swap the x and y and solve for y. The problem is, we can't solve for y. And no, you can't divide by b. It's not b times y, it's b to the power of y. So in order to solve for y, we create a new function that's the inverse of an exponential function. And for who knows what reason, we named the inverse of the exponential function the logarithmic function. So the way you'd read this is log base b of x, or y equals log base b of x. And that means exactly the same thing as saying that x equals b to the power of y. This would be what we call exponential form. This would be what we call log form. So if we have a function equals 2 to the x, just to keep things simple, the inverse function of that would be g of x equals a log base 2 of x. So the base of the exponent has to match the base of the log for them to be inverses of each other. And by definition, if we do the composition of a function and its inverse function, the result should just be x. So by definition, 2 to the log base 2 of x is x, and log base 2 of 2 to the x equals x. We'll see these again in a minute. What will really help you in this chapter is to be comfortable writing any exponent as a log and being able to write any log as an exponent. So the definition of a log means that it can be written as an exponent. The base of the log will be the base of the exponent. Whatever you're taking the log of will be the result, and whatever the log is equal to will be the exponent. I'm a visual person, so the way I like to think of this, if I'm trying to rewrite 6 equals log base 3 of x as an exponent, I take the base of the 3, base of the log, which is 3, swing it over to the other side. That pushes up the 6 and gives me 3 to the power of 6. The log drops off, and so it equals x. If I'm in exponent form and want to get to a log form, the base of the exponent is going to swing to the other side to become the base of my log, and then the x falls down. So x equals log base 2 of 3. A couple more examples. 6 equals log base x of 2 in log form. To rewrite in exponential form, swing the x over, push up the 6, x to the 6 equals 2. In exponential form, 3 to the x equals 2. Take the 3, swing it to the other side, becomes the base of the log, and we get x equals log base 3 of 2. Okay, some handy properties. And for me, I find it easiest to remember these new log properties if I think of them in reference to the exponential properties I already know. I know b to the power 0 is 1. If I take that, swing the b over to the other side, write it in log form, I get 0 equals log base b of 1. There's my new property. I know b to the power of 1 is just b. Rewrite that in log form. 1 equals log base b of b. b to the x equals b to the x. Rewrite in log form. X equals log base b, b to the x, which is one of the ones we did earlier. And the same thing with the log equals a log. Rewrite it in exponential form. X equals b to the log base b of x, which again we saw back on the first page where the base was 2. So some simple problems. 2 ways to think about these. We can simply remember our properties. And if we've got the log base 3 of 3 to the 6, that's this property here. I know it has to equal the 6. But another way to think about these, like this one here, log base 6 of 6 equals 1, is true by my second property here. But I could also take this and say log base 6 of 6 equals some number a. Rewrite it in exponential form, and I've got 6 equals 6 to the a, and from that I can tell a has got to be 1. And so I get the same result. Same thing here. You can memorize the property, or just set the log you're trying to simplify equal to some letter. Rewrite it in the opposite form. If it's in log form, rewrite it in exponential form. If it's in exponential form, rewrite it in log form. And then you get something that you can usually stare at and say, wow, the only way this is going to be true is if b is pi, therefore this function, this expression has to equal pi. Okay, graph of the log functions. Remember, we're define log functions to being the inverse of the exponential functions. Graphs of inverse functions are reflections across the line y equals x, and any point a beyond the function will have a point ba on the inverse function. So I'm going to take that table of values that I found for 2 to the x back on the previous video, swap all the x's and y's. And with that, I can come up with my red line, the graph of log base 2 to the x. So on 2 to the x, I've got a 0.01. So in the log function, I have a 0.10. On 2 to the x, I have a 0.12 right here. And then over here, I've got a function, a 0.21. And it can keep going with that. The 0.24 corresponds to the 0.42. And what happens with the log functions is we get a vertical asymptote, whereas the exponential functions had a horizontal asymptote. So again, smooth and continuous, x-intercept at 1, 0, and a point b1. Again, the reverse of the exponential. Vertical asymptote at x equals 0, the y-axis. Domain goes from 0 to infinity, not including the 0, and the range goes from negative infinity to infinity. We can do transformations once we got an idea what the basic function looks like. So f of x plus 1, add 1, shift the graph up 1. Log base 2 of x subtract 2 is going to shift the graph right 2, which is going to shift the vertical asymptote. It's now at x equal 2, and that's going to change my domain. Reflecting over the x-axis would be my blue line here. The red one reflecting over the y-axis, f of negative x. And then my vertical stretch right there. Okay. Two famous logs are the common log and the natural log function. The common log is the log base 10, and the natural log is the log base e. Now, both of these are important enough to create their own buttons on the calculator. By the way, the calculator does not have a button for log base 2, or log base 3, or log base 17. It only has keys for log base 10 and log base e. There's a way to trick it into finding log base 2. We'll get to that in the next section. And one thing that's important to notice is your calculator does a terrible, terrible job of graphing log functions. It has a really hard time with anything with a vertical asymptote. It just doesn't have the resolution. So I graph these on the calculator. I've got the log base 10. The common log is the lower one here. And then the one that's a little bit higher over here, that's log base e, the natural log function. And the way the calculator graphs it makes it look like it actually hits the y-axis there and stops. It doesn't. It will never reach the y-axis. It will never reach 0, but it will approach negative infinity. And the calculator just doesn't have the resolution. So this is the sort of thing I'm going to catch you on a test. If you don't understand what's happening with the graph of the log function, you cannot rely on your calculator to show you accurately what's happening.